Alright, in this video we are going to graph some more rational functions. In the previous video we did problem number 1 here. In this video we're going to do problem number 2. This is all grayed out weirdly. We're about to graph this problem. Alright, we're being asked to find a lot of different things, but you know what I like to do first? I like to do either the horizontal asymptote or the slant asymptote. These are kind of a pair because you can't have both. You're either going to have a horizontal asymptote or a slant asymptote, and it all depends on the degree. So let's go ahead and deal with these two right now. So looking at the degree, the numerator has degree 2, the denominator also has degree 2. So we have learned that when the degree is the same in the numerator and the denominator, then you can get well, first of all, there will be a horizontal asymptote when the degree is the same. And the way you get the horizontal asymptote is by looking at the leading coefficients, which in this case are just 1 and 1. And for the horizontal asymptote, it's going to be y equals, and we'll just do 1 over 1, which is 1. So that's what happens when they're the same. Now, if instead of a 2, this had been a 3, now we would have a slant asymptote. Alright, you get a slant asymptote when the numerator degree is 1 higher than the denominator. Okay, it has to be 1 more. Okay, what if it was 2 more? Alright, what if this was degree 4 or something like that? Well, then there would be no horizontal asymptote, and there'd be no slant asymptote either. Okay, so, but as it turned out, the degrees were equal, so we divided. If the top degree was less, like if this had just been x, then there'd be a horizontal asymptote of y equals 0. Okay, anyway, back to reality. So this is what it was, and so slant asymptote, none. There is no slant asymptote. Okay. Now, if we want to talk about vertical asymptotes come by setting the denominator equal to 0 and solving. But we have to make sure that what we think is a vertical asymptote is not going to get canceled out by something in the numerator. That's where holes come from, when things cancel out. So in other words, we're going to have to factor. Okay, so factoring is never going away. So please make sure you know how to factor. So x squared is going to be x times x. 4 can either be 2 times 2 or 4 times 1. Looking at the 5, I'm thinking 1 times 4. See how everything's positive? Okay, inner I have 1x, outer I have 4x. Together that makes 5. So there I factored it. Now the denominator, x squared, is x times x. 3 can only be 1 times 3. Now inner I have 1x, outer I have 3x. I'm shooting for a -2 middle. I will get a -2 if I have a -3 and a +1. That means this would be a +1 and this would be my -3. Okay, so if I was careless, I would say, oh look, there are 2 vertical asymptotes. X equals -1 from setting this equal to 0. X equals +3 if I set that equal to 0. But can you tell me why there will not be 2 vertical asymptotes? There will only be 1. I'm hoping you said the reason why there are not 2 vertical asymptotes is because these factors cancel out. So there's only going to be 1 vertical asymptote, and it's going to come from this guy on the right. It's going to be x equals 3. Okay, the one that canceled out, this is where holes come from when you cancel something out like this. If I set that x plus 1 equal to 0, I get x equals -1. But that's not a vertical asymptote. It canceled out. It's going to be a hole. So I will take that -1 and use it as the x value, it will be the x value of my hole. Alright, a hole is a single point. So for that reason, we're going to give it as an x and a y. So we still need to find the y value. Okay, so to find the y value, what you can do is take the part of your function that did not get canceled out, and you can substitute -1 for the x's. So what I'm going to have, if I put -1 here and here, then I've got -1 plus 4. Because remember, the whole function equals this. Y equals all of this. So right now I've got y equals -1 plus 4 and -1 minus 3. Okay, so that's going to give me 3 over -4. So that's the same thing as -3/4. So there's my whole, -1 comma -3/4. Alright, if you're not comfortable with this arithmetic, then you could use your TI-30XS multiview. Remember, x plus 4 over x minus 3. Fraction mode. So what was it? X plus 4 over x minus 3. So what did I want to know about? -1, an x value of -1. Alright, I'm in ask mode. I'm just going to stay in ask mode. So look, -1 is telling me -3/4. Alright, if it didn't say -1, I could have just typed in -1. Alright, anyway, I've got the whole. Now the domain is next. So for the domain, all I need, let me highlight what I need for the domain. Alright, for the domain, all I need to know is what are the vertical asymptotes and what are the holes. That's all I need to do the domain. So I'm not even going to do the whole graph. I'm not going to plot all these points until after I say the domain. Just to make a point, just to emphasize to you that I don't need it. So I have a vertical asymptote at x equals 3. Okay, so I'm going to have a vertical asymptote right here. And I have a hole at -1 comma -3/4. Alright, so -1, -3/4. So I have a hole like here. Okay, sorry, what was my vertical asymptote? At 3. So maybe I'll draw a little bit of my vertical asymptote. Whoa, too much. Okay, so I have a hole and a vertical asymptote at -1 and +3. I can get the domain just from this, nothing else, okay? Because my domain goes from left to right. So from left to right, my domain is going to go from -infinity to the hole. And then it's going to go from the hole to the asymptote. And then it's going to go from the asymptote to +infinity. That's how my domain is going to go. All right, so that's why my domain is going to go. I'll recopy this over there, but it's going to go from -infinity. Now the hole is at -1, so it's going to be -infinity to -1. Okay, that takes me from here to here. And now it's going to go from the hole to the asymptote. So that's going to be -1 to 3. Okay, now I'm going to do the remaining part, which is going to go from 3 to +infinity. That's going to be my domain. I don't even need to know what the graph is doing. I can get it just from the hole and the vertical asymptote. Alright, I'm just going to recopy this off camera. Alright, also we have a horizontal asymptote at y equals 1. So I went ahead and drew that horizontal asymptote. Okay, so the range can get a little bit more tricky than the domain. So I don't want to try to say the range without graphing it first, because sometimes it does strange things. Okay, so let's go ahead and plot some points now. So I got my x and my y. Look, people, look at this vertical asymptote. See how it's at 3? Do not simply do whole numbers. Don't just do 2 and 4 and 1 and 5. Do some decimals, people. Okay, have some guts. We need the information. So if the asymptote is at 3, I want you to give me a decimal to the left and a decimal to the right. That's the first thing I want to see. Stop being so scared, okay? You're not in elementary school anymore. You can handle some decimals. Stop crying, okay? Dry your eyes. If this is at 3, if I go a little bit to the left of 3, that's going to be 2.5. So I definitely want to see that on everybody's chart. A little bit to the right of 3, that's going to be 3.5. Okay? Hug the asymptote. It's lonely. Okay? Get close to it. After that, we can do the regular boring values, okay, which are also useful. So if I get another couple points to the left, would be like 2 and 1 would be good, and another couple points to the right would be like 4 and 5. Okay, just for fun, I'll go ahead and do 6 as well, just to fill out my chart. Okay, so I'm going to get these values off my calculator. Now when I type this into my calculator, it really doesn't matter whether I use my original function or if I use the version after canceling out the whole. Right, because I already have the whole recorded and whatnot. So everything else should be the same. So I might as well use the simple version, x plus 4 of x minus 3, especially since that's what's in my calculator right now. So let's go, giddy up. I'm going to stay in ask mode. So what do I want? I want 2.5 and 3.5 and 2. So 2.5 and 3.5 and 2. So I've got negative 13, 15, and negative 6. Okay, next I want 1, 4, and 5. Alright, that's negative 5 over 2, 8, and 9 over 2. Okay, you know what, but for these purposes, decimals would be actually helpful. So, negative 5 over 2, that's negative 2.5. And then 8. Nine over 2 is 4.5. And then 6. Alright, that's 10 over 3, 3.3. Okay, so I'm just going to take all these values and plot them on the graph. Alright, these pink dots are the points that I have plotted. Alright, some of them go way off the graph. Okay, that's 15, it's way up there. And negative 13 is down here. But enough of them fit on the graph. And don't forget this open circle, this hole at negative 1 comma negative 3/4. The curve is going to go right through that hole as well. So this counts as one of my points as well. So I'm just going to go ahead and draw my branches using the points that I've plotted and following the asymptotes. Okay, so your graph should look very much like this. Make sure you leave that open circle as a nice open circle. Okay, that's your hole. So when I do the range, it's going to work the same way that the domain worked, but instead of going from left to right, I'm going from bottom to top. Don't forget about the hole. Alright, the hole counts as a break in the graph. So I'm going to have to, when I do my range, I'm going to have to go from negative infinity up to where the hole is. Okay, and stop. So the part of my range, the first part of my range is going to go from negative infinity up to where the hole is. Okay, and then it's going to go from where the hole is up to the asymptote, little part there. Okay, did it just erase what I did? Quit it. Okay, so that green part is going to be part of my range. And then it's going to pick up after the horizontal asymptote and go the rest of the way up. So these colors sort of suggest to you what my range is going to be doing. Alright, the graph is going to go from negative infinity up to here. Now remember, the y value of this hole is negative 3/4. So I'm going to go from negative infinity to negative 3/4. And then I'm going to go from negative 3/4 to 1. That's the y value. And then I'm going to go from 1 to infinity. That's what's happening with the range. So what did I just say? What did I just say? Apologize if I sound hostile. I'm only playing. So it's going to be negative infinity to negative 3/4. Okay, that's the yellow part. And then it's going to be union negative 3/4 to 1. That's the asymptote. And then union 1 to infinity. Okay, that's going to be my range. Okay, I should have color coordinated it to match the colors. Anyway, what's left? Intercepts, the y-intercept. Alright, the y-intercept, you know that the y-intercept is always 0 comma something. That means we need the x value to be 0. The x-intercept is always something comma 0. That means we need the y value to be 0. Okay, so for my y-intercept, I can just let x be 0. So I can do that easily right here. If I let x be 0, that would mean I'd have 0 here, 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 and here. That's just going to leave 4 over negative 3. Okay, so if I let x be 0, I'm going to get 4 over negative 3, which is the same thing as negative 4/3. Alright, so I let my x be 0 and I get the y-intercept. If I let the y be 0, I get the x-intercept. Okay. Now, so if I let the x be 0, if I let the y be 0, that's the same thing as setting this whole thing equal to 0. Which is really going to be the same thing as setting the numerator equal to 0. It's the same thing in this particular case. If I set this equal to 0, then I've got x plus 4 over x minus 3 equal to 0. Now sometimes we say just set the numerator equal to 0. But look, all we're doing is skipping one tiny step. Because if I set the whole problem equal to 0, the first thing I'm going to do is multiply by the denominator. Alright? Well, I'm running out of space. X. Alright, but if I multiply by the denominator, 0 times anything is 0. So look what I get. Right away, I get x plus 4 equals 0. So all of a sudden, oh look, it's the numerator equal to 0. So if you've ever heard me say, if you want the x-intercept, most of the time you can just set the numerator equal to 0. All I'm doing is skipping a step, the step where you multiply by the denominator, because you immediately get numerator equals 0 anyway. Anyway, subtract 4 from both sides, I get x equals -4. Okay, notice I used the part over here after we canceled out the whole. If you had used the original equation, you would have gotten the same answer. I'm not going to go through it, but you can do it on your own if you want to. Okay, you made me forget what we got. -4, x equals -4. Okay, that means my x-intercept is -4, 0. Okay, now this time they're asking for increasing and decreasing intervals. Okay. Alright, let me get rid of this highlighter stuff. Okay, this part of the graph over here is decreasing because I got to look from left to right. This is going downhill. This part of the graph over here is also decreasing. Okay, so this entire graph is decreasing. So since the whole graph is decreasing, really the decreasing part interval is going to be the same as the domain. Okay, but please notice, because I have a whole, I'm not just going to say -infinity to 3. I'm going to say -infinity to -1, and then -1 to 3. All right, I still have to break it up. So so the decreasing part is just going to be the domain all over again, because it's the entire graph is decreasing. So I'm going to say -infinity to -1, -1 to 3. I'm just copying the domain, and 3 to infinity. All right, the entire graph is decreasing, but I had to go -infinity to -1. I had to stop there because of the whole. And then I had to go -1 to 3, okay, because I had to stop at the asymptote. And then I went 3 to infinity to go ahead the rest of the way. That's what happened. Okay, now I can't. I've lost my power to erase. That's not fair. Okay. What about increasing? Well, no part of the graph is increasing, so I'm just going to say none. There are no increasing intervals. Now, finally, end behavior. Oh, look, there's space for points down there. End behavior. End behavior is what happens on the left end and the right end. So please understand, end behavior, we're talking about this part of the graph and this part. We are not talking about, this up here or this down here, because this is the middle. This is not the end. End behavior is the left and the right. So as we go to the left, we're approaching the horizontal asymptote, 1. As we go to the right, we're approaching 1. So it's going to be 1 and 1. And guess what? The end behavior is always going to involve your horizontal asymptote, which is 1. Okay, so it's a no-brainer. End behavior. Okay, as we go to the left, function approaches 1, and as we go to the right, the function approaches 1. That's what we're saying for end behavior. And I already plotted my points elsewhere. Okay, so that was it for number 2.